So, hi everyone, I'm Andrei Văcaru. I'm a K developer mostly at Runtime Verification Incorporated, and today I will talk about formally verifying smart contracts, and I'll be using KEVM, which is a K implementation of the Ethereum virtual machine. It's fully faithful with other implementations, and it's also a K formal semantics, meaning that we can use it to do formal verification on Ethereum programs. So, as an overview, I'm gonna go and explain what K framework is, what formal verification and symbolic execution is, and then I'm going to show you what is our approach to formal verification and have a short demo session. So real quick, Runtime Verification Incorporated is formal methods company. We have serviced before clients in automotive and aeronautics companies. Now we're mostly focused on blockchain clients, and the general mission is to improve basically the state of security and the quality and the correctness of the code across the board. So, all right, what's K? So K is a mathematical modeling language. So basically you build mathematical models in K. One of the key features is that those modules are actually executable. So for example, you can take a test suite and execute it against the K Ethereum virtual machine, the KEVM, which is actually the mathematical model of the Ethereum virtual machine in K. And this also allows you to make proofs on it. So K has two backends which are currently in use. The LLVM backend, which is mostly for concrete execution, so it gives you a fast interpreter, and the Haskell backend, which is for symbolic execution. Okay. So, for example, if you were to say to wanting to make a new programming language, you could choose to write it either in C or in K, let's say. So if you choose to write it in C, then what you would get is a very fast execution, a very fast interpreter. But if you choose to write it in K instead, you still get execution, which is not as fast as if it was written in C, but you would also get symbolic execution, which gives you the ability to write proofs. So that's the reason you would choose to implement it in K. Also, the advantages are that you would develop a semantics for a programming language or that mathematical module, and you would save the implementation effort for multiple tools which K provides you. Also, for example, if you have multiple models in implemented, then upgrading one tool, like for example upgrading the compiler, would benefit all the other models which you have implemented in K. Okay. Now, formal verification, it's a pretty broad term which means different things for different people. Basically, formal verification is the process of checking that a design satisfies its system requirements. In other words, to check if the code behaves as expected using some formalism. So testing is a very good way to show the presence of bugs, but it can't show the absence of bugs. So as a scenario, you will write some tests, you would find some bugs, you would fix that bugs, but you have no guarantee that there are no other bugs in your contract. So to prove that there are no bugs, you have to do this mathematically, like a mathematical proof, which you do on a pen and paper, but this time we have computers, which help us very much because the proofs can get pretty big. So what do you need? You need the mathematical model of the programming language. As I said, we have the KEVM. The next step would be to have a specification of your program written in the same language. So basically, a specification is initially written in a very informal way, like an auditor has a chat with or sits at the table and discuss with the code developers, and they agree on what's the behavior of the code and what it shall do. So as I said, it's a manual process and it's informal. So the next step, it would be to take that specification and translate it into K. And since both the specification and the semantics of the virtual machine are both written in K, they would work very good together. And we would actually use the prover to see if the specification passes. So it's key to know what this gives you and what it doesn't give you. So people think like if the program is formally verified, then it's 100% safe, and this is not the case. When you're doing formal verification, you're verifying that a specific or a very exact specification of your contract is true. The same like you're doing testing. For example, you have a test which passes. That's very good. It means that scenario is working, but you have no guarantee about other scenarios. So like in testing, you have to think about all the corner cases and all the things you want to prove. Okay. So yeah, as an example, if you would have a proof on a transfer form function for an ERC20 contract, then this wouldn't give you any guarantee for an approved function or any other function of the token. Okay, so yeah, I'd like to talk a bit about symbolic execution, and I'm gonna go a bit back and forth with testing. So as I said, with testing, you're picking specific scenarios and you're just doing sanity checks for it. So let's say we have a contract, and this contract is in an initial state as 0, and it would have a function like deposit to deposit some tokens or I don't know, some value. And this function would have only a single argument. And in a test, you would write a test using a concrete value like 3. And this would have a very clear and specific execution path from start to finish. But in reality, most of the functions have also branching points, like if statements, require clauses, assertion clauses, and so on. So each branching point makes a different execution path. So you would have to take all the cases in consideration. So what symbolic execution does is it takes a symbolic value, an X in this case, like an identifier, and instead of going and iterating through all the values of the argument type, so for example, if in EVM we would have an EVM word, which would be a value somewhere between 0 and 2 to the power of 256. So instead of iterating through all of that values, we would have a single X value, symbolic one, and we would go through the execution process, and we would do some kind of analytical reasoning. So what you get is this entire space of execution path that encompass all the cases that X could take. And as I said, instead of looking at each execution path, we would do it in a closed form and analytical way. So in the end, we would get a single state description, but that state contains the symbolic value, and it would represent a bunch of states. Yeah, so, and again, holding a symbolic value would give would be a lot less resource intensive, because you wouldn't have to go, as I said, through all the possible values which an argument might take. Yeah, so again, testing can prove the presence of a bug, but because you have the specific execution trace that shows you the presence of the bug, it can't prove the absence of bugs because you're not checking any values there. So we're doing formal verification to get the entire diagram here. But you have to remember that formal verification, it's not a magic bullet. It's not like you're doing it once and your contract's secure. It will give you a high confidence only for the properties and symbolic tests which you have written. Okay. So, as I said before, we are using the KEVM, which is the key implementation of the Ethereum virtual machine. Here we have the repository. It would take some while to set up, so if you want to follow along, I suggest that you wait for this presentation to finish, and then you will have all the slides and this video, and you could follow along and do it yourself. So, as I said, is the full implementation of EVM. We tested it against the same test suite that other clients like Geth tested. Similar for Ethereum CPP and Ethereum JSVM, we use the same test suite for all the Ethereum tests. So we know that we have a faithful implementation of the EVM in our mathematical modeling language. So yeah, we also have release instructions. We have instructions if you want to build it from source. Basically, you would have to clone the repository, fetch all the submodules dependencies. Then you would have to run some make commands. But also very important is that if you choose to install it, please be sure to have all the system dependencies pre-installed before, or to install them first, because without them you wouldn't be able to run the make commands. Okay, so let's look over a specification. As I said, first I'm going to show the Solidity code, which is some kind of ERC20 token, but it's not correct. It has some bugs in it. So don't trust it and don't use it for any one of your projects. But yeah, you can see it has balances, allowances, it has the total supply, decimals, a name and a symbol. It has a constructor to initiate all those values. We have some getters and some of the ERC20 functions like transfer, allowance, approve, and transfer from. Okay, so basically this is the contract. The next step would be to have a specification. As I said, we need to know what the contract should do. So for this example, we would look at a few functions. So the decimal and the total supply functions should return the correct storage slot, and they shouldn't do anything else to the state of the program. So they're not supposed to change anything in the program, just returning the correct value. Okay, and then we have the approve function, which should update the correct storage slot, should do nothing else. And if we look at the code, the approve function has two requirements. So if either the owner or the spender is the zero address, then it should revert and shouldn't continue executing. In the other case, in which the owner and the spender are not the zero address, then the allowance of the owner for a specific spender should be updated to a specific amount. So basically, this is what the approve function does. All right. So this is our specification. The next step would be to write the formal specification, the one in K. So here I'm just having some snippets of it, which I'm going to show you right now. So this is how K configuration looks like, which is representing the state of the Ethereum virtual machine. And it's made out of what we call cells. So for example, we have a call data cell and the status code cell and so on. So here you can see that we're calling the decimals function, and in the K cell, you can see that we want to execute the entire program from start to finish. We want that all of the executions in all the cases, we want the status code to be a success. So we are not looking for reverts. We're expecting to program to succeed in all cases. Okay, and we also want the function to return in all the cases the decimals value, which is a symbolic value. And we can see here in the requirements down below that the decimals come from the account storage. So here we have the account, which is the contract, and we are doing a lookup inside its storage, looking at the decimals key, and we're taking that value and returning it. Also here in the first part of the operation, we're doing a bitwise operation because in the contract, in our contract, the decimals value is a uint8. So we're doing this bitwise operation just to take that specific 8 bytes. Okay. So that would be how a specification would be written. There should be other fields. For example, the specification also requires the program, the bytecode of the contract. So that would mean that you would first have to compile the bytecode with the Solidity compiler. Let me do it here. For some reason, it moves pretty slow, so this is the same contract, and I'm gonna use Sol-C to compile it. So this would actually be the bytecode of the contract, the binary part, which is also the compilation of the Solidity. So from Solidity, which is a higher level language, go to the bytecode, which is the input of the Ethereum virtual machine. So each byte represents an opcode and it's executed by the machine. So yeah, basically the next step would be to take this bytecode and put it into the specification, which I showed you snippets of, and then you would have to run the proof. So I already introduced the bytecode for the purpose of this presentation, and I'm just gonna run the prover. So I'm just gonna one second. Okay, so while the prover is working, it should take a while, a few minutes, because it's Oh, actually, I'm gonna stop it now because I skipped a step. So, yeah, here is the specification and how does it actually look like. One other advantage of the K framework is that you can write it in Markdown, and the code snippets which are actually executable are inside the K annotation tag. So basically, you can store your code and add documentation. It can be pretty easy from this point of view. So yeah, most of this part is boilerplate. Like there are some things required, but here is our claim, which was also in the slide. So the first part of the cells are, as I said, boilerplate. We're not gonna look into them, but they are still required because without them, the prover would complain. All right, so since I have multiple claims here, I'm just gonna comment out the ones which I'm not talking about, and I'm gonna keep only the claim for the decimals function. Okay, so now I can execute it. Sorry for that. Yeah, so this is, as I said, the decimal function. For the total supply, it should be pretty similar because it's also a getter. So basically, you would just copy paste the decimals function as a starting point. You would have to adjust the call data cell to call the total supply function instead. And you would have to adjust the storage slot lookup in the requires clauses. So, for example, here, this is the claim for the total supply. And you can see that we are now calling total supply instead. We're also returning the total supply value. We are still expecting success in each execution. And we're getting the total supply value from the storage, and we're gonna look at the total supply position. So this value is actually, I think I'm gonna go back to the Solidity code and explain. So when a contract is compiled and is stored in the storage, each of its fields is gonna be at some kind of index. So for example, and there will be counted from 0. So for example, balances would be 0, allowances would be 1, total supply would be 2, and decimals would be 3, and so on. So basically, this is just sugaring the value. Okay, and as I said, another key feature in the claim is that the account storage stays the same, and that's how we verify. So, for example, here in the status code, you can see that in the beginning, there is a value. There might be a value, which the initial value and how the cell is initialized. We do not care what that value is, but we care that in the end state, we would have a success. So it's actually a rewrite. Here in the
Hi, Andrea.
storage,
Sorry for the interruption. There's a one question.
yeah,
It's like Mohammed is asking, the bytecode are the opcodes, so he's kind of confused about the relationship here.
yeah. So actually, the bytecode is the numerical representation of the opcodes. So I think I have the opcodes here, the bytecode here. So for example, if I take this bytecode and go on to a website and look for, I think Etherscan has a pretty good tool, Etherscan disassembler. So basically here you would introduce the bytecode which is returned by the compiler, and you would decode it and have all the opcodes here.
Great, awesome.
Yeah. Okay. So let's look back at the proof. Okay. So we can see that the process returned a sharp top, which in our prover means that everything is okay. the proof is complete, and we have the guarantee that the decimals function works as expected and works as a getter should work. And it has no suspicious WS code which would change the state. Yeah. So going back to the storage here, as I said, the account here is where we check that the account storage doesn't change at all. So the way the storage was in the initial state is the same way the storage is going to be in the final state. Okay. So far so good, because everything is pretty straightforward, because we only have one case. There's no breaking points. There are no branching points. But let's look at the approve function, which, if we look at the code again, sorry for all the going back and forth. So yeah, as I said, the approve function has initially two values, but it's gonna call an internal function, and we're actually gonna look. Actually, the internal function would do all the work. So if we're just gonna look at the internal function, as I said, it has the two require clauses, and if the values are good and these conditions are met, then the allowance of an owner to a specific spender would be updated. Yeah, so if any of these would fail, then we would go into a revert case, basically. So, okay. That means that we have two cases: the case in which the values provided, the arguments provided work, and the case in which the function would have to revert. And we must specify both of them, because we care that the contract works as behaves as expected in both cases. So let's look at the specification here. So yeah, if we're looking at the success case, we can see that we are calling the approve function with two symbolic identifiers, two symbolic values. And as before, we are looking at the entire execution of the program, because we have no interest in starting the function at midway. This time the function, instead of returning a value, only returns true or false if the function behaves correctly or reverts. So in this case, since it's the success case, we are also expecting that in each execution the status code would be a success case. And okay, so in the contract storage this time, we have a rewrite, meaning that the account storage should be the same as initially. The only difference and the only update would be that for the allowance key, which is the position in the storage or the index of the allowance of the owner to the spender, in that case the amount is updated. So again, this is the successful case. So yeah, as requirements, you can see that we expect the owner and the spender to be in the range of an address. We're expecting the amount to be an integer, an EVM word, from which takes values, as I said, from 0 to 2 to the power of 256. And we're also expecting that both the owner and the spender are different than 0. So here is what where we are doing the check. Okay, so with this proof, with only this specification, we would look at, if I go back to the symbolic execution diagram, we would only look at a single part of this space, because since we haven't tested the case in which the function fails, we are not looking at all the corner cases and all the space of the values. So that is why it's important to take all the corner cases in consideration. Okay, so the revert case is pretty similar, but with a few key differences. We're also calling up the proof function with the symbolic values. This time we don't care about the output, so this is what this underscore means here. But at the status code, it says that we're always expecting a revert. The storage shouldn't change. And as a requirement, either the owner or the spender, one of them should be equal to 0. Yeah, and this should result in an EVMC revert always. Yeah, so basically this is how this is our approach to formal verification. Yeah, also what I wanted to say is that, for example, if you choose to, or you don't take into consideration all the cases, and for example, you forget to put these constraints. So for example, if you delete it or comment it, then the prover would throw out some error messages and throw out the configuration of the a configuration of the state in which the prover stopped. So I also did that before, and this is the configuration for the case in which we are doing the success case, but without the requirement that owner and the spender should be different than 0. So in the case in which they are commented, for example. Okay, so in that case, I know it's pretty big and pretty ugly, so I'm just gonna go through some key cells and explain them. So the key cell, which always shows the execution or the instruction at which the machine is, it's at hold. So since it's the same as in the specification, it means that the function executed completely and we're at the final state of the machine. Okay, so in the output cell, without the padding of the bytes, we can see that we have the message that the proof was from the 0 address, and we have a revert case in the status code. So the function reverted. Okay. If we also look at bottom at the requirement clauses, or where requirement clauses should be, we can see that the owner at line 100, we can say that the owner equals 0. So basically it showed us the case in which, or a counterexample in which the program failed, where the proof failed. So basically from this point, if I was writing this specification, I would look at the Solidity code, look why the program fails when the owner is 0. I would see the requirement clauses, and then I would update my specification to add the clause which I just uncommented, or I just commented. So yeah, basically this is how we do verification. Okay, so yeah, that's most of the presentation. I would also like to tell you that we have a tutorial for the K framework, which takes you from 0, from installing it, and it goes to all the way to proofs, which I talked about and presented you now. So if you want to learn K and it's appealing to you and you want to try it, you can try this tutorial. Okay. We also have, we are hiring. We are looking for a full stack developer and a technical writer to help us with the blog posts. The full stack developer should have knowings of Python and React.js. But if you want to try, send us your resume and we're gonna respond. And yeah, we have a Discord channel and a newsletter. If you have any kinds of questions about the K framework or the KEVM, then drop a question there. We will answer pretty shortly. So yeah, any questions or?